So maybe today we'll start with the notations and conventions. Okay. Notations and conventions. Now consider an n-dimensional space. If you have an n-dimensional space, then the coordinates of this space can be written as x1, x2, x3, etc. up to xn. So these are the set of coordinates for the space. Coordinates for the space. Okay. In general, we have a notation xi, and here we have to. You should not confuse this I with the power. Here I is just a superscript or index. So I is index, not power. For example, if you want to write square of any coordinate, then you have to use a bracket and then write the square. So here 2 is power, but here I is index. So that is the notation that we use. And similarly, in the last class, we have seen the summation, Einstein summation, right? So if an index is repeated in a term, then summation over 0 to n dimension, n is implied. That is automatically implied. An index which is repeated and over which the summation is implied is called a dummy index. Okay, for example, consider the transformation x mu, x prime nu. I can write x mu as a function of x prime nu. Then the derivative dx mu is partial derivative of x mu with respect to x prime nu, dx prime nu, right? So here nu is repeated. Nu is repeated. So an index which is repeated and over which summation is implied is called a dummy index. Therefore here nu is called dummy index. What is a dummy index? An index which is repeated and over which summation is implied. Is called dummy index. So a dummy index can be replaced by any other index which does not appear in the same term. So here there are two indices, mu and nu, right? In this expression you have mu and nu. Here nu is called the dummy index, and you can always replace a dummy index with any other index other than what is appearing in the term. So here mu is already appearing. So you cannot replace the dummy index with mu, but you can always replace the dummy index nu with any other index. For example, I can replace nu with I, j, k or alpha, beta, anything. But I cannot replace mu with any other index. And I cannot replace nu with the mu also. That is also not possible because that is already appearing in the term. Okay, so a dummy index can be replaced by any other index which does not appear in the same term. Then if an index appears only once in any term, then it has a definite value, a value between 0 and n. For example, in the same expression, you can see that mu is appearing only once in each side. In left hand side you can see mu is appearing only once, and in right hand side also you can see mu is appearing only once. So an index, if an index appears only once in any term, then it has a definite value. If it appears only once, then it has a definite value, and this value can range from 0 up to n, where n is the dimension that we have considered in that particular case. And such an index which appears only once in any term is called as the free index. Such an index which appears only once in any term is called as free index. Okay. Then next we go to the rank of a tensor. Rank of a tensor. The number of free indices of a tensor is called its rank. Okay. The number of free indices of a tensor is called its rank. So if you have a tensor T, mu, lambda, here you can see mu is a dummy index, right? Because mu is appearing twice. So mu is a dummy index. And nu and lambda are appearing only once. Therefore, they are the free indices, right? So what is the rank of this particular tensor? It will be 2, because rank is the number of free indices of a tensor, right? Here nu and lambda are free indices. Therefore, the rank of T, mu, lambda is 2. And vectors are tensors of rank 1. For example, yesterday we have seen the tangent T alpha, right? So here you have only one free index, that is alpha, right? Therefore, vectors are tensors of rank 1. Similarly, scalars are tensors of rank 0, because there are no free indices. Therefore, scalars are tensors of rank. Therefore, to really visualize the tensor or to know more about the novel aspects of tensor, then it will be seen only towards from rank 2 onwards. Okay, the novel aspects of tensor theory are seen from rank 2 onwards. So vectors are tensors of rank 1, scalars are tensors of rank 0, and to see more novel aspects of the tensor theory, they will be appearing from rank 2 onwards. Now, tensors are defined by means of their properties of transformation under coordinate transformation. So all these time we were explaining with respect to coordinate transformation, right? X mu going to x prime mu. So all the tensors are defined by means of their properties of transformation. What kind of transformation? Transformation under coordinate transformation. And therefore, they can be classified as contravariant and covariant on the basis of their properties of transformation. So how they transform? Properties of transformation under coordinate transformation. Tensors are classified as contravariant and covariant. So first we will see contravariant tensors. So before going to tensor, I think it is easy to visualize from vector point of view. Then you can always gradually extend it to the higher rank tensors. Okay. So since vectors are rank 1 tensors, we will start with vectors. So I will start with contravariant vector. Contravariant vectors. Now suppose we are given a curve in space and time, okay, which is parameterized by a curvature parameter sigma. So yesterday also we have, sorry, in the last class also, we have considered a curve with curvature parameter sigma. So thus the points along this curve can be represented as x mu, which is a function of sigma. So this curve, the points along this curve can be represented by x mu, which is a function of sigma. Sigma is the curvature parameter. And we have already seen the tangent to this curve, right? The tangent to this curve. So I am representing it now by a mu. Okay, the tangent to this curve, I am representing it by a mu is dx mu by d sigma. So here I am considering a 3-dimensional space time, therefore mu 3. Okay, so this is a curve which is parameterized by sigma and the points can be represented by x mu, and the tangent to this curve is given by a mu, which is the first derivative of x mu with respect to sigma. Now I am going to do the coordinate transformation. So x mu is transformed to a new coordinate x prime nu. Now in this new coordinate system, we have to define the tangent. Okay, so in this new coordinate system, the tangent A will be A prime nu. This is in the new coordinate system after the transformation. The transformed coordinates, we can write the tangent as A prime nu. And that will be the first derivative of x prime nu with respect to sigma, right? Now here one should remember that tangent is an intrinsic property of a curve. So given a curve, tangent should not change under the coordinate transformation. So the concept of tangent will remain the same. Only thing is that components of the tangent looks different in different coordinate system. That is the only thing. Okay. So one has to note that the tangent is an intrinsic property and it should not change. It should remain the same. Now the condition for the coordinate transformation is that the transformation is linear, continuous, and it should possess a second derivative. This transformation is such that it is linear, continuous, and it should possess at least second derivative. Okay, that is the condition for any coordinate transformation. So the transformation means I can write x mu as x mu, which is a function of x prime nu, and vice versa also. X prime nu can be a function of x mu, right? Now if I take the derivative of this transformation, then on the left hand side I will get the derivative of x prime nu, and x prime nu is a function of x mu. Therefore, with respect to, I'll take with respect to sigma because I need tangent. So I'll take with respect to sigma Yeah. So on the right hand side, it is a function of x mu, right? So here I have to take the partial derivative of x prime nu with respect to x mu. Then again I have to differentiate x mu, right? So d x mu d sigma. Now on the left hand side, you can see it is dx prime nu by d sigma that we have already defined here as the tangent in the transformed coordinate system, right? So a prime nu, which is equal to dx prime nu by d sigma, is the tangent in the new coordinate system. So I can write this as a prime mu. And this quantity, if you see, it is dx mu by d sigma is the tangent in the old coordinate system before the transformation. So I can write, so this is how the tangent transforms when the coordinate system is transformed. Okay, so this is the way how a tangent transforms when coordinate transformation is done. Now we have to see how it is transforming. So here you can see there is a prime nu and prime nu here. So a tangent always transforms in this particular way, and all the vectors that transforms in this way or the tangential way are called the contravariant vectors. Okay, so a tangent always transform in this particular way. So here there is a prime nu, here also there is a prime nu on the numerator. So here it is on the superscript, here it is in the numerator. So in this way, a tangent always transforms in this way, and the vectors, all the vectors that transforms in this way, that is tangential way, are called contravariant vectors. You can generalize this as tensors also. So all the tensors that transforms in this way are called contravariant tensors. Okay, because vector is a tensor of rank 1. So this is a simple way to show the contravariant vectors. You can always extend this to higher order tensors also. So in general, we can say if the components of a tensor transforms like that of a tangent, then the corresponding tensor is called as contravariant tensors. Now we go to covariant vectors. So we'll start with vectors. Consider a scalar function phi of x mu. A scalar function phi of x mu equal to constant. Okay, this can be any scalar function, for example, temperature. So x mu is the coordinate. For example, temperature at a point x1 or something like that, that will always be constant, right? So this is an example for scalar function. So consider a scalar function phi of x mu, and we describe a hypersurface. So consider a hyper where this scalar function is defined. For example, a surface like this. This is a hypersurface. So this is a hypersurface, and on the surface we have to consider a small area, and the normal to this surface will always be perpendicular to the surface, right? So I'll write like this. This is the normal to the hypersurface, and I am representing this normal as B mu. Okay, so normal is always perpendicular to the surface, and I am representing the normal to this hypersurface as B mu. And normal is defined as gradient of the scalar. So I can write phi of x mu with respect to x mu is the gradient of a scalar. Now we have to again consider the coordinate transformation. So the coordinate transformation is given by x mu going to x prime mu. Now under this coordinate transformation, phi of x mu will be phi of, now x mu is again a function of x prime mu. So x prime nu. Now this is phi prime of x prime nu. But we know that even under coordinate transformation, the scalar quantity will remain the same. The form will be different. You can see it is phi and phi prime, but the value will be constant. Therefore, we can see phi of x mu is equal to phi prime of x prime nu, right? This we have already discussed it in the last class. Now, in the new coordinate system, again you have to define the normal. So here I define B nu prime. This is the normal in the new coordinate system, that I can write partial derivative with respect to nu. Now what is the transformed one? Phi prime, right? Phi prime x prime nu. Okay. Now this can be written as partial derivative with respect to x prime nu. Phi prime can be written as phi of x mu, which is again a function of x prime nu, right? So phi of x mu, which is a function of x prime nu. Now I have to take the derivative. That will be, first I'll differentiate phi. So phi of x mu with respect to x mu, then x mu with respect to x nu. This is the differentiation. Now this quantity, partial derivative of phi of x mu by x mu, is the normal. See, normal in the old coordinate system, that is before transformation. So I can write this is equal to B mu. And this quantity is also there, x prime nu. So here left hand side we started with B nu prime. Okay, so we can see that the normal in the new coordinate system is equal to partial derivative of x mu with respect to x prime nu times the normal in the old coordinate system, right? So here you can see the primed quantity is sitting in the denominator, and here nu is also in the denominator. Okay, so a normal always transforms in this manner. A normal always transforms in this manner. That is similar to that of how a gradient of a scalar transforms. And the vector that follows this transformation are called as covariant vectors. Okay, the vectors that follows how a gradient of scalar, that is normal, are called covariant. So we'll just see contravariant and covariant, the difference. So here in contravariant vectors, the primed quantity is sitting in the numerator. On the right hand side, you can see the partial derivative of x prime nu, right? Here. This is contravariant, and in covariant, it is in the denominator. Here it is in the denominator, and you represent it as a subscript. See this mu and nu. And in contravariant, it is superscript. See, mu and nu. Mu and nu are superscript, and the primed x prime is always on the numerator. So that is the notation. Okay. So the vectors that follows the transformation of a normal are called as covariant vectors, and vectors that follows how a tangent transforms under the coordinate transformation are known as contravariant vectors. So the concept of covariant and contravariant vectors can be generalized to that of higher order tensors also. So we'll just write contravariant tensor of rank 2, how it transforms. Okay. A contravariant tensor of rank 2. For example, I can write T prime mu nu. So this is a contravariant tensor of rank 2. Why it is contravariant? Because I have written the indices as superscript. Indices are superscript. And this is rank 2. Why rank 2? Because the number of free indices is equal to 2. That's why T prime mu nu is a contravariant tensor of rank 2. Now, what is the transformation rule for a contravariant tensor of rank 2? For example, this tensor T prime mu nu is transformed into another coordinate system, then let it be T alpha beta. Okay. Then how does T prime mu nu transforms into T alpha beta and vice versa? Okay, you have to write. How do I write? It is a contravariant tensor. Therefore, the primed quantity should be in the numerator. So partial derivative of x prime. So first index is mu, right? So how this mu will transform? Though x prime mu, and this mu is transformed into alpha here. So I'll write partial derivative with respect to alpha. Now for the next index, here it is nu, and nu is transforming into beta, right? Dou x prime nu beta. So this is how you write the transformation rule for a contravariant tensor of rank 2. Similarly, you can write for covariant also. So how do you write? Covariant tensor of rank 2. So covariant in the sense the index should be mu nu. So rank 2 means there should be two free indices. So I am writing mu and nu. Now primed, and let in the other coordinate system let it be T alpha beta. Okay, I'm writing it as a subscript because it is a covariant tensor. Now, how does a covariant tensor transform? So here it is mu. Mu is going to alpha and nu is going to beta, right? So first I'll write for mu going to alpha. The transformation will be partial derivative of x alpha with respect to partial derivative of x prime mu. So here this mu is appearing in the denominator because it is covariant. The last case, see, mu is in the numerator because it is contravariant. That is the difference. Okay. And for this transformation, you have to write partial derivative of x beta with respect to x prime mu. So this is the transformation rule for a covariant tensor of rank 2. Now we can also have mixed tensor, contravariant, covariant and mixed tensor. Mixed tensor in the sense one index can be contravariant and other index can be covariant. Okay, so depending upon the rank, you can take any number of indices as covariant and any number of indices as contravariant. So it's called a mixed tensor. So mixed tensor of rank 2. Okay, mixed tensor of rank 2, how can I represent? T prime mu nu. So here one index, rank 2 means there should be, the free indices should be 2. So here mu and nu, and mixed tensor means out of that 2, at least one should be contravariant and one should be covariant. So I can write T prime mu nu. Now in other coordinate system we have T, alpha, beta. Now here mu is contravariant and nu is covariant. Okay, you should remember that. So mu will always transform like a contravariant and the index nu will transform like covariant. So first I'll write for mu. So mu is contravariant. So the transformation will be mu to alpha, right? Mu to alpha will be dou x prime mu, partial derivative of x prime mu with respect to partial derivative of alpha. And here it is covariant. Nu to beta is covariant. So I will write partial derivative of x beta with respect to partial derivative of x prime mu. So this is the transformation rule for a mixed tensor of rank 2. You can have other mixed tensor also. I'll write one more example. A prime alpha beta gamma. And one more thing you should remember while writing a mixed tensor, this gamma I should not write it here. Okay, this is wrong because we write the indices in a particular order. So alpha, beta, then only gamma should come here. Okay. Otherwise, you can write gamma here and alpha, beta. You have to give a little space here. Okay, this space you should not fill. Now it is not that important, but in some cases, the order of the index also matters. Therefore, you should never write one below the other. Then there is no importance. For example, like alpha, immediately below alpha, I should not write gamma. Okay, I should always leave a space. So alpha, beta, gamma. Now in other coordinate system, let it be mu, nu, lambda. Now here alpha and beta will transform like contravariant. So I'll write for alpha and beta. Partial derivative of x prime alpha with respect to alpha is going to mu, right? Then beta. Partial derivative of beta. Beta is going to nu. So x nu. Now gamma is covariant and it is going to lambda. So how do I represent? I can write partial derivative of x lambda with respect to x prime gamma. Okay, so this is a mixed tensor of rank 3. This is a mixed tensor of rank 3. Okay, this is how you write the mixed tensors. Now this difference between covariant vectors, contravariant vectors and mixed tensors will not be visible in the Euclidean space. So that's why all these days we did not learn about the difference between covariant and contravariant. This will be visible only in the non-Euclidean space. Okay, therefore we cannot differentiate between covariant and contravariant tensors in Euclidean geometry. Okay. Now we'll do a simple problem based on this. Question is, show that velocity vector is contravariant. The question is, show that velocity vector is contravariant. So whenever a question with covariance or contravariance come, first thing you have to write is first you have to define the quantity. Here quantity is velocity, and then immediately you have to write the transformation, because the contravariance or covariance is based on the coordinate transformation, how the quantity transforms, right, under the transformation. So first I will define velocity. So velocity v. Now it is a vector. So therefore I have to write an index. So v mu I can write. Okay. So velocity v mu is dx mu by dt. Right. Velocity is defined as rate of change of displacement. So dx mu by dt. Now how does this change? X mu will transform to x prime nu, right? So x mu is a function of x prime nu. Otherwise I can write x prime nu is a function of x mu, right? Now I will define the velocity in the transformed. So after the transformation, let it be v prime nu. Okay, this is after the coordinate transformation. V prime nu will be partial derivative of x prime nu with respect to dt. Okay. Now this quantity I can obtain from differentiating this transformation. So I am x prime nu is equal to x prime nu, which is a function of x mu. So differentiating both sides, I will get with respect to t. Okay, differentiating both sides with respect to time. Here I will get dx prime nu is equal to, now on the right hand side it is a function of x mu. That's partial derivative of x prime nu with respect to x mu, then dx mu by dt. Now you can see this quantity is v prime nu here. Here you have. And on the right hand side, partial derivative of x prime nu with respect to x mu. And this quantity is v mu that we already have here, right? So therefore, how does it transform? Velocity is transforming as a contravariant vector. You can see this primed quantity is sitting in the numerator, right? Therefore, it is proved that velocity is a contravariant vector. Velocity is a contravariant vector. So this is a very simple problem. Now you can also write higher rank tensors, right? I'll just mention higher rank tensors. You can add any rank, okay, keep on add. For example, higher order contravariant tensors. Contravariant. T prime mu. Not only mu, I need mu, this is rank 1. So rank 2 means I have to write nu. Rank 3 means some lambda. Rank 4, rank 5, etc. I can write any number, right? So that is known as higher rank tensors. That can be represented as prime mu with respect to alpha. Why I am writing alpha? Because here I have alpha, right? Similarly, so as you add the more number of indices here also you have to add that much transformation, and also here also you have to add, for example, mu, nu, lambda. So alpha, beta, gamma, and etc. Many things you have to add. So these are known as higher rank tensors. Similarly, for covariant case, I can write T prime, mu, then etc. and T, alpha, etc. Partial derivative of alpha with respect to mu and etc. So for each transformation you have to write. So these are higher order. And similarly for mixed tensors, I can write T prime mu and etc. Similarly nu etc. Now that is transforming to T alpha and beta. Partial derivative of x prime mu. Partial derivative. And first you have to write for all the contravariant. Okay. Then I'll write for all the covariant. X beta, x prime nu, and for all the other covariant. So this is how you represent higher rank tensors, higher rank contravariant, higher rank covariant, and higher rank mixed tensors. Okay. Then equality of tensors. I'll take for 5 more minutes and I'll wind up. Okay. Equality of tensors. So you cannot equate tensors with different rank and different type. Tensors of same rank and same type are said to be equal only if there is one-to-one correspondence between them. Okay, for example, you have A, alpha, beta is said to be equal to B, mu, nu only if alpha is equal to mu and beta is equal to nu. Okay, otherwise you cannot equate two tensors. For example, you cannot equate A alpha with B. No, you cannot do this. This is wrong. Okay, so tensors of same rank and same type are said to be equal only if there is some one-to-one correspondence between them. Okay, so A alpha beta is equal to B mu nu only if alpha is equal to mu and beta is equal to nu. So tensor equation is an invariant equation. Should always remember that tensor equation is an equation. Okay, one more small topic I'll take. Zero tensor. In a given coordinate system, a tensor is called a zero tensor only if all the components of the tensor is equal to 0. Okay, for a tensor to be a zero tensor, all the components of the tensor must vanish. For example, T mu nu is equal to see here all the components are 0, right? So zero tensor means all the components must vanish. Then this tensor is a zero tensor. Otherwise, it is not a zero tensor. Okay, it is important to define the zero tensor because if you want to do addition and subtraction, for example, the tensor algebra is defined only if you have a zero tensor. For example, if you need an additive inverse, then you need zero tensor. To describe an additive inverse, you need a zero tensor. So that is the importance of the zero tensor. Okay, is called as zero tensor only if all the components of the tensor vanish. Okay, and it is important to define the zero tensor to describe the additive inverse. It is important to define the zero tensor to describe the additive inverse. Okay, so that's all for today. We'll stop here.